Welcome to Just Enough Assembly for Compiler Explorer. My name is Anders, and I work here in Norway, where I'm also broadcasting from, in a company called Zivid, where we make these cool robot eyes. And I mostly write C++, but a couple of other languages as well there. And we are hiring, so if this kind of thing sounds interesting, hit me up on Discord or something after the talk. I also run this C++ quiz site called cppquiz.org, which I think is fun to do. And I hang out on Twitter a bunch on these various accounts, Knatten, CPPP quiz, and AffectiveCpp. So you can reach me there if there's anything you want to chat about. But yeah, we're not here to talk about any of that. We're here to talk about Compiler Explorer and assembly code. And why? Like, if you haven't used Compiler Explorer, it's a really cool site where you can just paste your C++ or your Rust or C or whatever on one side of the screen. And then on the other side of the screen, you can see the assembly code that gets generated. And why would you want to look at assembly code? You're probably not writing any assembly code, so why do you want to look at it? Oh, you write your C++ for other humans to read, and then the compiler translates that into some machine code to run on the CPU. And for every CPU instruction, there's an assembly instruction. So if you can look at the assembly code, then you can see what the compiler did to your code. What exactly did it do to all your fancy C++? What is actually going to run on the CPU in the end? And you can try out different compilers, different compiler options, and play around and learn quite a lot of things, I think. But let's just have a look at the site instead of just talking about it. So here is Compiler Explorer. And then to the left, you can see I've written some C or C++ code. Don't worry about the contents of that code. It's just random example code. And to the right, we can then see the generated assembly code. And up here, I can try out a bunch of different compilers. It's a long list of different compilers. And I can put in whatever compiler options I want in here as well. And then Compiler Explorer is going to be helpful and highlight all of the assembly code for me. And if I move my cursor around in the C++ code, you can see the assembly code that was generated from those instructions being highlighted, and also the other way around. So it's a really convenient way to look at your code. But there's a lot of stuff here to understand, like all these move things and these D-word putters and RBP and a lot of what's really going on over here. It's quite a lot to look at initially. But in about 50 minutes, you will understand everything that is on the right-hand side here. And not only what each instruction means, but also why did the compiler decide to put exactly that code in your assembly here. And that's not going to be because I'm going so fast through everything. It's actually not that hard. So we'll just start really slowly from the very basics and then build up so you can get an understanding of all of this code. And then hopefully you'll have like a good foundation to understand more of your own code when you start putting that into Compiler Explorer. So I'll go back to my slides again. Right, and yeah, as I mentioned before, please use the Q&A feature on Zoom if you have any questions. And then today we have, like most of the slides are this kind of toy emulator sort of thing. So we're going to have this little x86-64 slideware emulator here. We're going to look at the CPU and the memory and see what's going on. So in the middle of the screen, I have visualized the CPU. And the CPU has a bunch of registers. And to really do anything interesting with data, you first have to get them into the registers in the CPU. And for each of the examples here, I'm only going to display the registers that are interesting to that particular example. So for my first example here, we have two registers called RDI and RSI, just arbitrarily picked for the example. And I'll just not show the other ones just to keep the slide a bit tidier. You can see I have the register name here and then the contents. So these are 64-bit registers, which I then show in hex because that's just a convenient way to display it. And you can also see I have zeroed out the registers. So in real life, when your function gets called, the registers just have whatever was in there from before. But just to make the examples clearer, I zero them out at the beginning, but that does not happen in reality. Right, then let's get some assembly code up. And again, every slide is going to have some assembly code to the left. And assembly is a really simple language. It's not necessarily easy, but it's simple. It's just like one instruction after the other. One line, one instruction. You have the instruction name and then 0 or more operands. So here we have 3 instructions in this little program. And I've also put up this little orange step debugger indicator kind of thing, so we can just step through the code and see what happens on the CPU. Okay, so the first instruction is a move instruction. And just like in C++, in assembly, move does not mean move. So in assembly, move means copy, right? So we're going to copy something here. We're going to copy RDI 2. So do we then copy RDI into 2 or 2 into RDI? That's the question. And I think the answer is quite obvious. We're going to copy the value into the place rather than the other way around. And there are 2 different flavors of assembly that are popular. So it's Intel assembly is the one I'm using here. It's a default on Compiler Explorer. And yeah, the most popular one these days, it seems. So move RDI2 means then take the value 2 and put it into the RDI register. So if we execute that line, we get the value 2 over here in RDI. Then we can move RSI 4. So we're going to take the value 4 and put that into RSI. So then we have our 4 over here. The next instruction is an add instruction. And we're used to saying like auto result equals A plus B. But in assembly, there is you don't get to specify the where to store the result. So you can see it only says add RDI RSI. So it's going to add those 2 together. And it's always then going to store the result in the first operand. So we're going to take our 2 and our 4 and make that result put that into RDI. So it's more like an plus equals kind of thing. So RDI plus equals RSI. So if we execute that, we can see we got our value 6 in RDI. Right, that was the first example. And remember to just ask questions using the Q&A feature if you have any questions. That was registers, but you only have that many registers and they're not very big. So right, if you want to do something really interesting, you need to have memory as well. So I'm also visualizing some memory here now to the right. And in all of the examples today, we're just going to look at the stack. But anything I say about memory addressing in the stack is also true for the heap or for global data and whatever really. So except for pushing and popping or anything that has to do with like specific addressing of memory works for any kind of memory. So we'll just use the stack for all of that today. And we are on x86-64 here, and the stack grows downwards on my architecture here. So we can see I put the address to the left, just truncated it like these are 64-bit addresses, but I don't want to waste that much screen space, so I'm just truncating it to the last 2 bytes of the address. So you can see we have higher addresses here at the top. So B3, B2, B1, and then the stack grows downwards like this, down here to A1, A0 here at the bottom. And we can see the contents of each of the bytes at those addresses. I've also introduced one more register called the RSP, or the stack pointer. So the stack pointer points to the current top of the stack. And currently it points to B0, which is here. And I've also put this little indicator here to point to the top of the stack, just to visualize it a bit more so we can see where the current top of the stack is. All right, so let's first set RDI to a number that's easy to see. So we could just move RDI and this really long value just to have a value in the register. And then we can try to put that on the stack. And now we can see the push instruction only has one operand, which is which register to push. So it doesn't say how many bytes, where in memory or anything. It's just going to put that 64-bit register onto the stack at wherever the stack pointer is pointing. So it's a 64-bit register, so we're going to push 8 bytes onto the stack. And the only remaining question then that you can think about, it's not so easy to have an interactive session here, but what is the value going to be of this byte when you push this onto the stack? So there's one right answer, there's one plausible but wrong answer, and then there's the just wrong answers. Let's see what happens if I push this onto it. It ends up being FE. So that's the correct answer. The other plausible answer would be that it would be 10. right? It could, instead of going FEDC, it could have gone 1032 and so on. But we are on x86-64 here. It's a little endian architecture, so we're going to take the least significant byte and put it on the lowest memory address. So 10 is our least significant byte of this number, and it ends up down at the lowest address over here. You can also see that it then bumped RSP to now point to A8, and you can also see this visualized over here. So it made room for this and bumped the stack pointer so we can keep pushing more stuff onto the stack. And then, of course, we can also pop stuff from the stack. So I'm going to pop now into RSI. And again, you can see we don't say how many bytes to pop or where to pop it from. It's from the stack pointer, and it's the size of the register. So we're going to pop then 8 bytes into RSI. And we can see we got those bytes in here. And we can see that our old values are still here on the stack. So yeah, it doesn't like remove anything or clean up anything like that. Okay, so we have a stack that you can push and pop values onto and from. And that's you can actually do quite a lot just with a stack machine like that. But what you typically want is to be able to arbitrarily address your memory like in any normal program, right? So let's just get some values into RDI and RSI, like this. And then let's see what we can do with specific memory addressing. So now we have a bit more of a complicated move instruction here. It's still actually the same that we've seen before. You have the move instruction, and then you have 2 operands, like this. The second operand we recognize just RSI, the name of a register, so that's what we're going to move from. But then the question is, what are we going to move it into? Where are we going to put this value? And we're going to put it at keyword putter RSP -8, whatever that means. So inside of these square brackets, I can put any, or at least almost any kind of arithmetic expression saying where do I want to put my stuff. So I say RSP -8 just to have something simple. So that will be RSP, which is B0, -8 is A8. And then that's over here. So we're going to compute that address. But that is a value. So RSP -8 is a value, so you can think of that as a pointer. And then you need to dereference that pointer. So that's what you do with a keyword putter thing. Keyword putter will kind of dereference this pointer into like sort of like a reference that you can put something into. And what does keyword putter mean? So putter means pointer. What about keyword? So a byte is 8 bits, and then you have 16 bits, which is a word, and you have a double word, which is 32 bits, and then a quad word, which is 64 bits. So a 64-bit pointer to a 64-bit value will then be a quad word pointer or a keyword putter. So if we do this, RSP -8 is A8, and then we take the value of RSI and put it onto that address. We can see we got all of these 3s over here. But now we haven't pushed anything onto the stack. We just said, take this place in memory, stick the bytes over here. So you can see RSP did not change. We didn't change the stack really. We just happened to put them in that memory. And now we have a variable. So if you had like a local variable long L in C++, this is exactly how that would look like. You would get these bytes onto the stack like this, with something like this move instruction here. Yeah, and you can also use memory addressing and all sorts of other instructions, not only move, but for instance in add, as we have here on the next line. So I can do exactly the same here, keyword putter RSP -8, and use that on the right-hand side, and then I'll read that value and put it into RDI. So if I execute that, you can see we got, or if I go one back, RDI has a bunch of 2s, and we have at RSP -8, we have a bunch of 3s, so we add those together and I get a bunch of 5s in RDI. And now we know how to write and read local variables. Right, so before we continue with the next example, I just want to say a few things about register sizes. Yeah, so on x86-64, all the registers are 64 bits, but we can also use smaller parts of them. And originally on the 8086, you had 16-bit registers. So we had these AX, BX, CX, etc., which were 16-bit registers. But you could also address just like the high and low, AH for high and AL for low parts of this register. So if you write to AL, it's the same register as AX. You're just going to overwrite the lower half of it and just leave the high part of it. And then you got the 386 with the 32-bit architecture, which now gave you the EAX and so on registers, and you still kept the old ones as like views into that register. And then you got the x86-64 with 64-bit values and 64-bit registers like RAX, RBX, and so on. But yeah, you can still use all of the other ones for smaller things. And again, since I like quizzes, the next quiz question is, how big is an int? So we're on a 64-bit architecture, and an int is 32 bits. So when they bumped to 64-bit registers, they didn't want to change the meaning of an int because that would break a lot of programs and it like double the size of anything. And yeah, so we still have 32-bit ints. So what can you put in these registers? You can put a signed or an unsigned long here on 64 bits. Well, this is like by default on x86-64 Linux, normal everything, where you don't do anything crazy. And signed and unsigned ints in the 32-bit ones, and the signed or unsigned shorts in the AX ones, and so on, and then signed, unsigned, or just plain chars in the AH and AL, and so on registers. But yeah, this is up to the implementation, but on like a normal x86-64 Linux kind of thing, this is what you get. Right, so let's do the same example that we just did, but let's do it with 32-bit registers instead, just to see how that changes things a bit, and also because ints is just really the most common data type, I'd say, like the default data type, sort of. So let's do the same example with ints. And now we can see we're doing ESI and EDI instead of RSI and RDI like we did before, but we still visualize the full registers over here. So you can see the full RSI and RDI over here. So if we start with those two instructions, we put these 3s into ESI. You can see we just wrote to the lower half of RSI and right to the lower half of RDI. So now we've moved just these 4 bytes instead of all the 8 bytes into these registers. And you can see in the move instruction, we also have ESI again. And this time I say RSP-4 instead of RSP-8, because I'm only going to need 4 bytes for this. So I'm going to just use these 4 bytes here. But inside here, RSP is still the 64-bit RSP, not ESP or anything like that, because the addresses are still 64 bits. It's just that the values I'm using are now 32 bits, or they could be whatever number of bits I want really. And you can also see the Q word has changed to a D word for a double word. So that's just a name for a 32-bit value. So if I do this, I move the contents of ESI into memory here. And then again, I can use the add thing. So we have EDI, a bunch of 2s, and D word putter RSP-4. So we have these 3s, add them together, and we get a bunch of 5s in the first operand, which was EDI. So then we know how to read and write ints as well. Right, but writing and reading single ints and longs, that's not really enough. We want to have more data. We want to have arrays, and arrays are also a good motivation to talk about a bit more complex memory addressing, which is interesting. So yeah, for this one, I'll just use 16-bit values just to save some space and just to demonstrate some different things. So now we're going to use word putters for 16-bit values, and I'll just put these values into memory first. So I have two bytes which are 1111, which go over here, and then a bunch of 2s and a bunch of 3s and a bunch of 4s that I just put into memory at specific offsets from RSP. So now we have 8 bytes in memory, and assembly does not have types at all. So these are just bytes. Okay, so these could be 8 individual bytes. There could be 1 long. They could be part of a network packet or what have you, right? We don't know what they mean, but in this program we're going to treat these 8 bytes as 4 16-bit values, so 4 shorts basically. And anyone who's been doing C or C++ know that like an array, that's almost just a pointer, right? Anytime you want to do something with an array, what you want typically is to have a pointer to the first element. So let's have a first pointer to the first element, and put that into a register, so we can have that register like pointing to the first element. How do you get a pointer to something? Is because we've seen how to compute an address. So we can do this RSP minus 8 to get the address, but then we have always dereferenced it with a keyword putter or a dword putter or whatever. But now we want the actual address. And to get the actual address, we're going to use the LEA instruction, and that's the load effective address. So LEA is going to then do the same computation that we've seen before here. So it's going to take RSP minus 8 and get A8. And it's going to, instead of writing to that or reading from that, it's just going to take the address and store it into the first operand, which happens to be RDI in our example. So RSP minus 8 is A8, and let's load that address into RDI. So now RDI is a pointer here to our first element in the array. And the first element of the array is basically the array, right? And then imagine you want to access the fourth element in the array, right? So then we have to skip past the first 3 elements times the size of the element. So that's 6. We're going to go past 3 times 2 bytes for each, so we're going to go past 6. And we want to take that element and put it into AX. So now we're using a 16-bit register in AX. And then we do word putter RDI plus 6. So RDI is our pointer which points down here. We add 6, and then we get a E over here. And then we use the word putter thing again to dereference it, and we get that value into AX. So these 2 4s were now copied into AX here, which is the lower 2 bytes of RAX. But now we have hard-coded, like not only the index, but like the index times the size of, so the very, like exactly which byte in the array we wanted to get data from. And we don't want that. We want to be able to parameterize this. We want to have, for instance, a register specifying which element of the array do we want. So let's use RSI as our index. So then we have RDI as the base pointer, and then we want to use RSI to index which exact element do we want. So let's say we want the first element, so we put just 0 into RSI, move RSI 0, just put 0 in there. And then we can do a bit more complex arithmetic in here to pick out the value. So we can say we want RDI, which is the base of the array, plus the index times 2, because 2 is the size of the element. So every element in our 16-bit array of 16-bit values is 2 bytes long. So if we do RDI plus RSI times 2, we have RDI pointing down here, and then RSI, which is 0 times 2 is 0. So we still get, oh, did I do something wrong here? RDI plus RSI. Oh, this is first, yeah, the first element is a bunch of 1s, so that's correct, yeah, of course. We got a bunch of 1s over here. But now the good thing is that we have parameterized the index. So if I now do inc RSI, I'm going to increment our index over here, which is, remember, it's 0. We increment that to 1. And then I can use exactly the same instruction that is on the previous line. So these 2 instructions are exactly the same. And now I can do again RDI plus RSI times 2. RSI is now 1, so 1 times 2, that's 2. RDI plus 2. RDI here plus 2 over here. So we get these 2s, and we can move those into AX. And that's really nice, because now we can use the exact same instruction for looking at different parts of the array. So we don't have to hard code any indexes or anything like that. Everything is parameterized, and that's something that's really useful to do in anything like a loop or a conditional kind of thing, or yeah, anything like that. And I think that's a good transition into conditionals. So the first conditional we're going to look at is if. So we want to compare 2 numbers and just see if the first one was bigger than the second one or not. So let's first get the numbers in that we want to look at. Let's put 3 into RDI and 2 into RSI. So now we have these 2 numbers, and we want to somehow compare them and see if RDI is bigger than RSI. I want to store true in RAX. So I'm going to put a 1 in RAX to represent true. But in assembly, we don't have any nice if or else or switch or anything nice like that. We basically have comparisons and goto. And since goto is considered great, we can do a lot of nice things with comparisons and goto. So the first thing we do is the CMP instruction, which is a comparison. So CMP for compare, and we say compare RDI to RSI, please. And if we execute that line, you can't really see anything changing. It doesn't really do anything that you can observe directly here. So comparison just compares these two numbers and stores a bunch of metadata about that comparison. And then you have conditional jump instructions that can be used to do stuff based on that metadata, which was stored away in some flags in the CPU. So if we want to see if RDI was bigger than RSI, we can use the JG instruction, which means jump greater. So JG is just going to see, like, you did a comparison and it stored away some metadata about that comparison. So I can now go look and see was the flag set that indicate that it was greater. So JG, jump if greater, and it jumps if it was greater. So in this case, it was greater, and we jump over to the greater label down here. And then we do move RAX1 because we want to put 1 to represent true in RAX, which will be our result. So we get 1 over here in RAX. What if it was the other way around? So now this is the same example again, but I'm going to store 2 in RDI and 3 in RSI instead, so that the first operand is not greater than the other one. So put 2 and 3 into RDI and RSI, and then I compare them. Again, nothing happens when I compare it with the CMP command, that we can see directly at least. But then we get to the jump greater, and this time it was not greater. So we don't jump, we just fall through to the next instruction. And the next instruction is then move RAX0 because we want to store false in RAX because the number was not greater than the other one. And now, importantly, we have to do an unconditional jump, the JMP jump, because if we didn't have this the unconditional jump here, we would just fall through to the next instruction over here, move RAX1. So we'd also execute the other branch of the if statement. So we have to just jump to the very end of the entire if thing and jump down here to the end. And this is something you see quite often with assembly, that you kind of have the else block here above the if block. So it's kind of the other way around than what we're used to seeing often. Right, so there are many ways to do this compare and jump. And first you compare the numbers, and then you can do like jump equal, jump not equal, jump if less or equal, and all of those things. And then, as I said, assembly doesn't have any types. So assembly doesn't know if your types or if your bytes are supposed to represent a signed integer or an unsigned integer. So the same bit pattern, like if I take 2 bit patterns, depending on whether you treat them as signed or unsigned, one might be greater than the other. And if you have a negative number, it typically has the first bit set to 1. And if you have unsigned ints, that means it's a really big number. But if you have signed ints, it means it's a negative number. So you can't just compare the bytes. You have to say whether you want to treat the comparison as signed or unsigned. So we have different instructions for unsigned comparison. And less and greater were taken, so they went with below and above. So you have jump below or equal, jump above or equal. So that's how you do unsigned. And the way it all works really is very simple. You have the CMP instruction, the compare instruction. It's just going to take the second operand and subtract it from the first one, and not store the result anymore. Just do the subtraction and not store the result. And if a subtraction instruction results in 0, then you have the 0 bit set in the flags register. And if the second was larger than the first, then we end up with a negative number. So then the sign bit gets set in the flags register. So when if I want to implement the jump equal instruction on my CPU, I can just check what's the 0 bit set. Because if I subtract 2 equal numbers, then well, the result is 0. So I can just check for the 0 bit. And similarly, if I want to check if it was if it was less, for instance, I can just look at the sign bit and so on. So that's how comparisons and conditional jumps work. Okay, then we have variables, we have arrays, we have memory addressing, we have conditionals, but we also need loops. And assembly doesn't have if, else, switch, any of that. It of course doesn't have for, do, while, any of that niceness either. But we can still basically compare and go to, right, with our conditional jumps. So let's do move RCX1 first and see if we can make a little loop here. So we're going to do a loop and use RCX as our loop counter. Okay, so we'll start iterating at 1. So RCX as the counter register. And we're gonna accumulate some result somewhere. So let's just use RAX for the result. So we just initialize that to 0. Okay, and then we can start iterating. So our counter is now at 1, and we say we want to count up until 3. And then what we do to do that is to first start our for loop with comparing, is our counter equal to 3? So compare RCX to 3. Is it equal? No, it's not. We have 1 and we want to loop until we get to 3. So then we just we do not jump and we just fall through into our loop body. And just to have something to do in the loop body, I figure I'll just accumulate all the loop indices into RAX. Right? So we'll just add the counter RCX into RAX. So add RAX, RCX. We'll then sum those and put the result in RAX. And then I want to do the I++ kind of thing in my loop. So I'll increment the counter with inc RCX, and now it's 2. And then I have to unconditionally jump to the beginning of the for loop. And then we say, are we 3 yet? We're not, we're 2. So the jump if equal does not happen. And we just fall through. We add 2 to RAX, increment our counter, jump to the beginning of the for loop, compare to 3. Are we 3 yet? This time we are actually 3, so we stop the loop and jump to the end for label here down at the end. And we're done with the loop. So if you want to look at this as C or C++ code, we have basically int RAX equals 0 over here. Then we have int RCX equals 1 here. Then we do RCX not equal to 3, which is these two. And then plus RCX, that's the inc here, and RAX plus equals RCX, that's the addition here. And then finally we have this jump to the beginning of the for loop, the label, which is basically the end curly brace of the for loop, right? So now we have loops as well. Then it's time for a real example. So here we have a super simple little function called sum. So it takes 2 ints a and b, adds a and b, and returns that, right? Int sum a and b, return a plus b. So what I want to do then, I want to just copy all of this assembly code over here into our little slideware toy emulator kind of thing, and just step through and see what happens and see if we can understand what all the stuff is. Right, so this here, the assembly code here now is exactly what we saw on Compiler Explorer, just copied in here. And the first question to ask is, like, how do you get A and B? Well, where do you get A and B from? How do you get that into the function? And I'm on Linux, or I wrote a talk on Linux. I'm on a Mac right now, but what you use is the calling convention. So all systems have a calling convention, and Linux happens to be using the System V AMD64 calling convention. And Microsoft has a similar calling convention, slightly different, but very, very similar. And the calling convention specifies, among other things, how do you get stuff into a function? How do you pass arguments? And what the System V AMD64 one says is, if you want to just pass a couple of ints, just stick them in some registers. And that's really nice. We can just, like, as you can see here, let's say someone called us with the values 2 and 3. They will have put the 2 and the 3 for the values of A and B into RDI and RSI. So the calling convention says which registers to use as well, of course. And that's really nice, because if I want to call this sum function, I'm already doing stuff with my data, and I can just leave the data in some specific registers and then just jump to this function. And that's very efficient, rather than me having, for instance, to like put them into some specific place in memory or push them on the stack or anything like that. If I can just leave the data in the register and just jump in here, it's going to be super fast. So that's really nice. So someone have put A and B into RDI and RSI and then called the sum function. And the first thing that happens in the call function is this push RBP thing. You can also see I have some more registers here now because I just visualized everything that GCC happened to use in the code that they generated. So RBP is the base pointer. It's actually just a general purpose register, but we kind of always use it as a base pointer to our part of the stack. So RBP is going to point to our part of the stack, and the calling convention specifies that if you do anything with RBP, if you change RBP, you have to restore it before you return, because whoever called us, they were probably using RBP for something. So if you want to write to RBP, we better restore it at the end. So you can see we're pushing it here, and the last thing we do before returning is to pop it again. So whoever was using RBP gets their value back before control returns to them. So if you push RBP, RBP would have had some value, just zeros here, but now RBP has been pushed onto our stack, like here, and RSP has been incremented. And now starts kind of our part of the stack. So then we take a copy of RSP into RBP. So RSP is the stack pointer, and here is where you're allowed to kind of start from. And then we copy RSP into RBP. So now we have two stack pointers. The reason you want to have two stack pointers is very often in a function you are going to push stuff on the stack, you're going to call other functions, you're going to do something that changes RSP. So the official stack pointer is going to jump or up and down during the execution of your function. So if you can then just take a copy before you start doing all of that, then RBP will be just a stable pointer that doesn't change. So during the entire function, you have one pointer that always points to the beginning of our part of the stack where we can put all our stuff. And in this example, we are not actually changing RSP. So RSP doesn't change during this function, but GCC always emits this preamble kind of thing where you do it just in case. And of course, when you optimize your code, all of that goes away. So then RBP is pointing to our start of the stack, and we can start doing stuff. And then you can see like all the addressing here goes relative to RBP, and not relative to RSP. Right. Let's then get our. Let's see what GCC decided to do. So we just wanted some RDI and RSI, but what did GCC do? Well, it decided to put EDI and ESI onto our part of the stack. So at RBP -4 and -8, we get the values of 2 and 3. And that's not really necessary to just sum them. We don't have to put them there, but having put them there means that now they are actually L values. They are real variables that we can take the address of. So if they were just left in registers, we couldn't take their address. They're not really L values. So just to be able to do that and have them as proper variables and being able to inspect them in a debugger and whatever, let's get them into here. And then we can just optimize it away if you compile with optimization options later. Then GCC decided to take those two values from memory that we now have and put them into EDX and EAX here on the two next instructions. So we will just do RBP -4 and 8 to get the value of A and B into EDX and EAX. So now we have them back over here. And then finally, we add them together. So finally, we're getting to the body of the function, which was return A plus B. So we're going to add A and B with add EAX, EDX. And remember, the result is always stored in the first operand. So we get a 5 here in EAX. Then we are going to pop RBP, as we said in the beginning. Since we overwrote RBP, we'd better restore it for the caller. And then we return. But how do we return? Like we have a 5 here in RAX, and we want to return it. How do we get it out of our function to the caller? Should we put it in memory, or what do we do? So the calling convention again specifies what to do, and the calling convention says if you are going to return a simple thing like an int, just put it in RAX. So RAX is the return register, so we have to put it there. But luckily, like this, well, not this one, but this add instruction here already put the result in EAX, so we don't have to manually put it there. It's already where it's supposed to be, and we can just return control to the caller, and then the caller can just start looking in RAX and keep working with the data in registers. So no memory really involved in passing our values either into or out of our function. which is very nice for performance. So that was a very cumbersome way to add two numbers. So if you go back to Compiler Explorer again, we can start playing around with the site a bit and see what happens, for instance, if we do -02. And that does seem a lot better. No memory usage, a lot fewer instructions. This looks nice, but you recognize this one, LEA. That's the load effective address instruction that we saw earlier, which we use to find an address. And we're not interested in addresses, we're just interested in adding two numbers. And it turns out that LEA is a very convenient thing, because assembly doesn't have types. LEA, it has like the only mission of LEA is to just do some math over here and put the result over here. So you remember the add instruction, you can't say where the result is supposed to be. But with LEA, you can actually specify where the result goes. So now you can just add these two numbers and put them into the return register in one instruction. So we don't have to add them. If you just added RDI and RSI, you would have the result in RDI, and then you have to move it into EAX. But now you can just do that in one instruction. So that's a very nice thing to do. And LEA is also a super common instruction, which has been designed to be really fast. So we can really quickly, in one instruction, do the addition and specify where do you want the result to be. All right, back to the slides again. Yeah, there we go. So now we've seen variables, memory, arrays, and functions, at least a function being called, but we also want to look at how to call a function. And with all of that knowledge, we can finally arrive at the holy grail of programming paradigms, which is, of course, procedural programming. So let's have a look at an example where we actually have one function calling another function. So we have here our one function called times2. So the times2 function just takes an int and it returns that int times 2. So times2 takes int I, return I times 2. And then we have something very similar to our sum function that we had before. So we have sum times 2. It takes A and B just like before, adds them together just like before, and then passes the result through times 2 before returning. Sum times 2 takes A and B, and then sums together A plus B and doubles the value and returns it back. So if you then take all of this stuff over here and copy it back into our slides, we get this. And for this example, we are going to need more memory because GCC decided it needed some more memory. So remember, the stack was growing down like this, and I've just like continued it over here. So you can see it's growing down A2, A1, A0, 9F, 9E, 9D, and so on, down on the other side. So this is just basically just the stack growing downwards. I just had to like wrap it around to fit it on the slides. Yeah, so let's get going. The first thing we do is to push RBP, but because remember the calling convention said you can't overwrite this register, someone might be using it. So let's do that first. And then we go move RBP RSP, which we also saw on the previous slides. Just take the stack pointer and put it into RBP so we have a stable base pointer. And this time that's actually useful because we are now doing, on the next instruction, we're going to do sub RSP 16. So we have the stack pointer pointing to somewhere, and we subtract 16 from it. Let's just do that and then we talk about why. So subtract 16 from RSP, so now we have RSP pointing down, pointing over here. And RBP is now our stable base pointer. So that means anything in between RBP and RSP is now our part of the stack. So here we can do whatever we want. If we then at some point call another function, they will start picking up RSP using the stack from wherever RSP is. But we've set aside 16 bytes here to use for whatever we want, or whatever GCC decided they wanted. And again, whoever called us wanted to use the values 2 and 3 for A and B. So they have put 2 and 3 into RDI and RSI for the two first integer arguments. And again, just like before, GCC is taking the values from EDE and ESI and putting them onto RBP -4 and 8. So if you execute those two lines, we'll have our A and B values over here. And then GCC decided, okay, let's put those values back into some registers, just like on the previous slide. So we decided to put those values into EDX and EAX. And then it has to do the addition. So it does the A plus B, add EAX, EDX. Then you get 5 here in the results in EAX. And now it's our turn to call a function. And then again, the calling convention says the first int argument to a function goes in EDI. So we have our temporary result 5, which is the result of A plus B. We want to pass it to the times2 function. So we copy then the value from EAX into EDI, which is the first int argument register. Okay, so now we got the 5 over here in RDI. And now we can call the times2 function. So we do call times2. And then the instruction pointer is going to change to down here to the first instruction of times2. And then we can start doing our times2 function, which again does the push RBP, move RBP, RSP. We've seen many times now. And again, it takes the first int argument, puts it into memory. So it moves it over here. So we have this 5 in memory, which is now a proper L value. And then it moves it back into EAX. And even on O0 here, GCC decided, well, if you want to multiply something by 2, let's just add it to itself. It's going to be faster. So the I times 2 thing is just add EAX to EAX. So now the value 5 that we have will just be doubled, and it becomes A. And it conveniently is already in the return register EAX, so we don't need to move it into there in any way. We can just return. And to return, we will pop RBP. You can see RBP was restored over here. So we don't overwrite it, which is nice when we get then return when we get control return to our sometimes2 function. It's nice to have our old base pointer back. And then we return and our control jumps back here. And now we have the result of the times2 function. We have it in RAX. And that's really convenient as well, because what we want to do, we want to return it. So we have to make sure it's in RAX. But, well, times2 already left it in RAX, so we don't have to move it any more around in that way. It's just where it needs to be. So we can just leave and return. And leave is a new instruction that we haven't seen before. And leave is just going to basically restore RSP and RBP. So it's going to first restore RSP. So leave is basically just reverting these two things. So we did move RBP RSP, so it's going to just do the opposite thing to move RSP RBP. So that we have restored RSP, and then it's going to do pop RBP to restore RBP for the caller. So leave is just a shorthand thing to do both of those things. And then we return to whoever called us. So let's have a look at optimizations again. So we had quite a lot of code here. Let's do O2. And that really helped a lot. So if you again look at, if you look at the times2 function first, you can see that we again see the EAX thing here. So it's going to take the argument in RDI times 2. So again, LEA is doing that with just adding it to itself. And you can then specify you want the result in RAX, because that's the return register. And in the sum times 2 function, it's getting EDI and ESI as the two arguments. It's adding that. The result will end up in EDI. And then it's not calling times 2 even. It's just inline this function. So we can see just doing the LEA directly in here to double the value and put it into the return register and then returning. And in fact, if we just hide this thing from the rest of the world, so it's only internal to this compilation unit, you can see that that function is not even emitted by the compiler. So just inlined, and it never sees the object code at all. Okay, then it's time for to go back to this first example that we looked at, which we have here. So this is the thing I said, don't worry about it in the beginning. And here's all the assembly code that we looked at, which we probably thought was a lot. And then I promised you that you would be able to understand what it means and why it's there. So let's see if I could keep my promise. So we have this computer function, which takes an A and a B, and it then just decrements the B until it's, as long as it's larger than 0, and just accumulates the result in A. And then it returns the value of A. So it's a useless function, but it demonstrates all the things we've learned today, basically. So if you look over here at, you can see here it says computer. It's just a label to say this part with assembly comes from the computer function. We see the preamble with pushing RBP, move RBP, RSP, which we've seen many times. We see that it takes the first two ints in EDI and ESI, puts them into our stack frame. RBP is the base pointer, so we have proper variables in memory. And then comes the for loop. And JMP is an unconditional jump. It's jumping down here to L2, where it compares something to 0. So ESI, that was our second argument, that was B. So B now lives at RBP minus 8. So down here, we compare B to 0 to see if B is larger than 0, which was the conditional thing in the for loop here. So if it's not equal, if it's larger than 0, we jump to L3, which is the loop body. And RBP minus 4 is A, and this is B. So then we move A and B into these two registers, add them together. And then, since we want to store this value in A, we have the sum of A plus B here now, and then we have to put that back into memory where A lives. So that's here. And then we're going to do minus minus B in the for loop here. So we do that by subtracting sub 1 from RBP minus 8, which is where B lives. And then we get back to the comparison again. So if B is now 0, we compare it to 0, jump if not equal. Well, if it was equal, we'll just fall through down to here. We'll take the value A, which is at RBP minus 4, and move it into EAX. And then we pop RBP to restore that value, and then we return. And since I had some technical issues at the beginning, I don't have time now to go through the caller function, but it's very much the same thing. The only difference here is that we can see this, it's setting aside space on the stack with subtracting 16 from the stack pointer. And here we can see it calling the computer function. And we can see an if statement where it's doing I'm less than 10 over here. So it's implemented that by comparing it to 9 and jumping if it was greater. Instead of jumping if it's less than 10, it's jumping if it's greater than 9. So yeah, the links are there in the slides if you want to look at it, but basically it's just stuff that we've already seen. Yeah, so some tips. You can hover over the instructions if there's something you don't understand, and then you can Google if the tooltip doesn't give you enough information. If you want to use Compiler Explorer, always make a local standalone reproduction first. So use your IDE or whatever to just make one CPP file which contains everything, and then strip away everything you don't need, and then paste it onto Compiler Explorer. Maybe you have some tools in your IDE to inline stuff. Compiler Explorer has a bunch of libraries, so it has like Boost, FMT, Eigen, Catch2, whatever, so you can actually use those on Compiler Explorer. And you can even include GitHub links, like normal hash include on a GitHub link. That's really nice. Always start out using ints instead of complicated types, and then when you understand what's going on, then you can like swap in your proper types that you were interested in looking at. And of course, don't try it on your full project. This is a tool to, you have a specific question and you ask Compiler Explorer what the answer is to this particular thing. You don't use it to inspect your whole code base. And if you have any other tips, then please share your own tips in the Discord chat after. All right, then I think we'll just finish here, and then I'll see you on Discord. And thank you very much for coming.